That's all right. Al, in the future, I think we'll typically have the homework due in class anyway. If I can remember, I'll try to bring a sample, but yeah, I'll just be extra cautious about all of these pages this time. So how was everyone's weekend? Just a normal weekend? Okay, fine. Yeah, I didn't have many people ask me any questions about the homework. I mean, everybody feels pretty good about it, I guess. Okay.
Hi.
Hi. I was just asking if the implication is true that not many people ask me questions about the homework. Does that mean everybody feels pretty much okay about it?
I think so.
Okay.
I think pretty okay.
Yeah, great, that's good. Happy to hear. Just, silence is no indicator, right? To make sure that you feel okay. Okay. Right, so, on the subject of homework, a few of you just turned it in now. And that's fine. You can turn it in early if you want. But in case you don't, remember, I'll just remind you to turn in problem set 1 into the envelope on my office door, 540 A Nightingale, by 3:15 tomorrow. Of course, you can, if you like, or on Canvas. Okay, so just remember to do that. Right, so last Friday we were in kind of close to the end of this discussion of how we can use the complex exponential in conjunction with the polar form of a complex number to derive all kinds of trigonometric consequences. In fact, the very last thing we did was produce a formula for the triple angle formula for cosine, right? We deduced the formula for the cosine of 3 times theta in terms of cosine theta and sine theta. So let's just do another useful thing along those lines, and then we'll move on. So I just want to do one more example. So you might remember this, coming up against this in calculus 2. Let's ask you to compute the integral from 0 to 2 pi of cosine to the 4th theta d theta. Okay? You learn a couple things. You learn how to deal with things that look similar to this in calculus 2 when you start to discuss integration. But frustratingly, not all things of this form, some trigonometric function to some power, are tractable with the methods you learn in calculus 2, right? In particular, there's some nice things that happen with tangent, right? Because you can express that as sine of theta over cosine theta, and then do some substitution or something. So there's no great way to deal with this from the methods of calculus 2, right? Maybe if you're really clever, but let's try to use complex analysis, what we've learned about complex numbers so far, to try and integrate this. Okay? So, first, let's write, or remember the fact that cosine to the 4th of theta is just equal to the real part of the complex number with modulus 1, e to the I theta, raised to the 4th. Right? Now, we also derived some formulae, or actually we didn't really do much derivation. We just plugged in the complex number e to the I theta to our old formula for the real part of a complex number to get e to the I theta plus e to the negative I theta over 2 is just the real part of this complex number, right? And we raise this to the 4th. Or, if we like, we can just pull out the factor of 1 over 2, raise that to the 4th separately, and just have e to the I theta plus e to the negative I theta raised to the 4th. Okay, so now let's, we have a binomial raised to an integer power. So we should think of maybe just using the binomial theorem. See if we can use any identities that we've derived to simplify things. Okay, so then by the binomial theorem, what do we get? We get 1 over 2 to the 4th is equal to e to the 4I theta plus 4 times e to the 3I theta times e to the negative I theta plus 6 times e to the 2I theta times e to the negative 2I theta plus 4 times e to the I theta times e to the negative 3I theta and one last term here, plus e to the negative 4I theta, it's our last term. Okay, is what we get from applying the binomial theorem with our exponent 4 to this binomial. So now we can simplify these multiplied terms, right? Just by using our usual rules of exponents. Yeah? So, still have my factor of 1 over 2 to the 4th in front. And what I get here now is, well, there's no simplification for my first sum n, e to the 4I theta, plus 4 e to the 2I theta. Right, that is to say, I just combine these exponents, right? 3I theta minus I theta, this is 2I theta. Okay, plus 6, yeah, again, the exponents are additive inverses of one another. Plus 4 e to the negative 2I theta. Plus e to the negative 4I theta. So now I can combine terms which have opposite sign exponents and see what I get, right? And you'll see shortly why I do that. So let me just bring my 6 out to the front, and then I'll collect terms that have a coefficient of 4 together, because that gives me e to the 2I theta plus e to the negative 2I theta, and then I'll collect terms which have a coefficient of 1. E to the 4I theta plus e to the negative 4I theta. Sorry. Okay, why did I do this? Yeah?
You can turn them back into cosine of 2 theta and cosine.
Yeah, these are just 2 times the real parts of this complex number, right? And 2 times the real part of this complex number. Yeah? Which is equivalent to what you said. Yeah, we'll eventually turn them back, one more step after that, we'll turn them back into cosines. Okay, so we get 6 plus 4 times 2 times the real part of e to the 2I theta plus 2 times the real part of e to the 4I theta, sorry. Okay. Well, in particular, we can turn those back into cosines, right? We'll have 6 plus 8 times cosine of what's my argument here now is just 2 theta, right? So cosine of 2 theta plus 2 times cosine of, now my argument is 4 theta, just the non-I part of my exponent, right? Okay. Well, we know, yes?
Can you just explain again how it went to the 2 times the real part?
Yeah, so remember our formula for the real part of,
Oh, I mean,
so yeah, I just forgot this 2 in the denominator.
Yep, okay, thank you.
Yep. Okay, so yeah, certainly we know how to integrate constant and some cosines, right? So let me just remind you, right? This is equal to cosine to the 4th of theta, right? That's what we started with. So let's evaluate our integral. fourth theta d theta is equal to the integral from 0 to 2 pi of 1 over 2 to the fourth times 6 plus 8 cosine 2 theta plus 2 cosine 4 theta d theta. Okay, well, how do I integrate this? Well, first of all, I take my constant multiple out front, right, 1 over 2 to the 4, and then I get what, 6 theta plus, well, technically really I have to do a substitution here, right? But what I end up with is 4 sine 2 theta, right? Plus 1/2 sine 4 theta evaluated at 0 and 2 pi. And if I do this substitution and arithmetic, what I get is 1 over 2 to the fourth times 12 pi, or just 3 pi over 4. Okay, so really, to me, the hardest part of this is just, in light of what we've been doing, is remembering the binomial formula, right? And then I guess there is something to say having the insight that this is 2 times the real part of the complex number 2I theta. Okay, so this is also going to be thematic as we develop calculus for the complex numbers. We will be able to address certain problems from the theory of integration of functions of a real variable, which we were not very easily able to address before we introduced complex numbers. Okay? And I'd also like to point out that we actually haven't developed any of the theory of calculus for complex numbers yet. These are just properties of the geometry of complex numbers, right? I haven't really said anything about how to take the derivative of a complex function, or what that means. And if all goes according to plan, we're going to lay the technical foundation for that today. Okay? But before we do that, there's one more topic about the algebra and geometry of the complex numbers that I wanted to talk about briefly. So remember on Friday, we had this result called De Moivre's theorem, right? Where we learned how to, we gave a formula for how to take positive integer powers of a complex number with modulus 1, right? Which employed the complex exponential. So let me just say, we can slightly extend De Moivre's theorem for arbitrary complex numbers Z and integer n. Simply by saying z to the n is equal to r to the n, where r is the modulus of z, times e to the I n theta. Okay, that is to say, the exponential, the complex exponential allows us to express any complex number as its modulus times a complex number with modulus 1, right? So then we know from Dumont's formula that, in fact, this is just equal to r to the n times cosine n theta plus I sine n theta. Okay, so that is to say, for any non-zero complex number, of course we can invert the modulus and take the nth power of that, and that's what a negative integer power of a complex number would mean for the modulus. And then sine and cosine are equally well defined for negative multiples of theta, right? Yeah?
Could you extend instead of an integer, could you consider all values for n? Like,
All what values?
so, all rational values?
So that's exactly what we'll do now. Okay? This is the question. We can extend to negative integers. What can we say about rational numbers, specifically of the form 1 over m for some integer m? Yeah? So, we'll now ask, what can be said if we consider exponents of form 1 over m, for m an integer. Well, so if we want a complex number, we'll call it zeta. Okay, this is a lowercase Greek z. I have a hard time drawing this, but it's denoted this for historical reasons. So it comes like this, and then this. It's like a Z, but it's got a big belly middle center part. Okay? So we want a complex number zeta. Write that down. Zeta. Satisfying the following relation: zeta to the m equals z. Okay? And then what we'll do is define that the nth root of z is zeta. Okay, so we're trying to solve the opposite problem of determining what raising a complex number to 1 over m is by defining a complex number that satisfies this, and then we'll define the meaning of what it means to raise a complex number to 1 over m by this construction. Okay? Okay. Then define z to the 1 over m to zeta. Okay? So, I mean, notice right away. Oh, we can write zeta equal to the nth root of the modulus, sorry, I guess I should say modulus of z, right? Times e z I theta divided by m, and this satisfies our equation star. Okay, so it's seems almost trivial, right? We've just applied the usual rules that we would expect for exponentiation. But there's a subtlety here. Okay? However, consider that the number 1 in the complex numbers, in fact, even in the real numbers, has 2 square roots. One and -1. Now, consider also, and furthermore, one has 4, I should actually write this out, 4 fourth roots, which correspond to the square roots of the square roots of 1. Okay, so in other words, we found 2 square roots, right? We know this from a long time ago. So what are the square roots of 1? Just the same, they're 1 and -1. Okay, we get 1, -1. Now, what about the square roots of -1?
I negative I.
I and -I, yeah, right. Because now we're looking in the complex numbers, right? We're allowing a complex number output to the equation 1 raised to the 1/4 power. Okay? So, we also have I and -I. Okay? I'll write this. These all solve 1 raised to the 1/4 power is equal to zeta. Or, put another way, zeta to the 4th is equal to 1. Okay, now, take a second to think back. On the first day, we talked about how once we move to the complex numbers from the real numbers, all polynomials with real coefficients become solvable. In fact, if you look at a polynomial of degree n, it has n solutions. Right? We're looking at a special case of that right now. Zeta is our variable, and we have it to the 4th power. There are exactly 4 solutions to that. Okay? Okay, so there's some subtlety, right? How do we know which of these roots to choose? In the real numbers, when we take square roots, it's conventional to just choose the positive square root. But even if we don't, we know there's only two choices, right? So now we're in a bit more of a predicament, because as you've shown, or will soon show on the homework, things aren't so simple in the complex numbers as positive and negative, right? There's no order to the complex numbers. So we should proceed further with our investigation of what, if any, geometric content is behind the multiplicity of solutions to, in this case, the equation zeta to the m is equal to 1. We'll start with. Okay? So, let's do something that's maybe kind of pedantic and silly, but I think it could be helpful. Let's look at what happens in the polar form of each of these four complex numbers when we raise them to the fourth power. And then what we'll do is pictorially draw what happens with that sequence of multiplications. Okay? So, in polar form, notice that we have 1 raised to the fourth power is equal to, well, okay, so we have modulus 1 and e raised to the I. What's the argument of 1? Capital R, I guess. 0. 0, yeah. Raised to the fourth power. This just gives you 1 times e to the 0 equal to 1. Okay, that is exactly what we expected to happen, right? Okay, how about negative 1? How does when you raise negative 1 to the fourth power? And take this intermediary step where we express negative 1 in polar form. Okay, so again, we have modulus 1, right? And then we have e to the I. What's the capital R of negative 1? Is pi, yeah. Right, it lies on the negative real axis. There you go. Pi radians around. I get there. So let's see here. Raised to the fourth power is just sorry, 1/4 times e to the I 4 pi. Now, of course, 4 pi is an integer multiple of 2 pi, right? So e to the 4 pi I is also equal to 1, right? Now, if I'm being super pedantic, I forgot to put a 4 there. Whatever, 1 to the 4. Okay, so how about if I raise I to the fourth power? Okay, again, I get modulus 1. E to the I, what's an argument of I?
Pi over 2.
Pi over 2, yeah. Pi over 2. Raised to the fourth. We get 1 to the fourth times e to the I 2 pi. Okay, again, this is a integer multiple of 2 pi off from 0. So I get negative I to the fourth. So I got 1 times e to the I. Now, the principal argument of negative I is negative pi over 2, right? But instead, I'm just going to choose the argument to illustrate a certain point. I'm going to choose the argument 3 pi over 2. Okay? Lowercase r. Okay? So I get 1 to the fourth times e to the I. 4 times 3 pi over 2 is 6 pi, right? Which is an integer multiple of 2 pi off of 0. We get 1. Okay. So we have this pattern kind of emerging, right? We get 0, pi, 2 pi, 4 pi, and 6 pi. And we have the first 4 integer multiples of 2 pi added onto 0 in order to get these 4 complex numbers, right? Okay. So graphically, let's look at what's happening. So first, let me look at the powers of I. Okay, so what's I times I? Negative 1, yeah. So my first multiplication of I times I is negative 1. What's I times negative 1? Negative I, yeah. So my second multiplication gets me here. Now, what's negative I times I? Is just 1. So this is my powers of I. Let me just make that more explicit. Here I have I squared. Here I have I cubed. And here I have I to the fourth. Gets me about back to 1. Okay? Now, let's take a look at, probably a little too close. Let's take a look at the powers of I squared, which, of course, is negative 1. I squared times I squared gives me I to the fourth, which is just 1, right? So I get I squared squared equal to 1. Now, if I multiply by I squared again, I get back to I squared. Okay. Interesting. Let's continue this process of generating this type of diagram. Okay, I think I can fit one more in here. Okay, let's look at the powers of I cubed. What's I cubed? Is just negative I, right? Okay, so we start here at I cubed equal to negative I. What's I cubed times I cubed? Negative 1, I to the 6th, or negative 1. Yeah. Okay, so I to the 6th, or negative 1. Okay, what's I to the 6th times I cubed?
I.
It's just I to the 9th, or I, okay? I to the 9th is just equal to I. Now, what happens if we multiply I cubed by I to the 9th?
1.
Yeah, we get I to the 12th, or 1. I to the 12th, that looks like I wrote the equal sign in the exponent, but I meant I to the 12th is equal to 1. Okay, so again, we took 3 steps, but this time we traversed the vertices in a counterclockwise fashion, where with I, we did it in a clockwise fashion. Again, very interesting. So, just for completion, let's look at I to the 4th. Okay, so I to the 4th is 1. What's I to the 4th squared? 1. I to the 8th, or I to the 8th times I to the 4th is I to the 12th, which is equal to 1. Okay, so it's stationary as we take powers. Remember this? This is going back, I should have said this at the beginning. This is going back to our geometric interpretation of what it means to multiply complex numbers. Right? We're adding their arguments together. And because all the complex numbers we're dealing with have modulus 1, we're staying in the unit circle. Right? Okay. So I'd also like you to note, that the roots of the equation sorry, I always need a day or two of practice before I get good at writing zetas on the board again. The roots of this equation form a square. It's not a very good square, but this is no coincidence. Let me tell you that. So, let me tell you how we can generalize this. We're working with the number 4. We consider the roots, the 4th roots of 1. Okay, so in general, the number of nth roots of the number 1 is m. There are mth roots of the number 1. And we call them the nth roots of unity. That is because 1 is often called the unit. It's the unit for multiplication. So this is just another way of saying that mth root is 1, but everybody still says this as though it's a different thing. It's really just the mth roots of 1. Okay. And we have the formula. One to the 1 over m is equal to e to the I times 2k pi divided by m, or written in sines and cosines, cosine of 2k pi over m plus I times sine of 2k pi over m, where we're letting k range from 0 up to m minus 1. Okay? So, y up to m minus 1, and start at 0. Well, look back to our pictures here. The case where k equals 0 corresponds to 1 for the fourth roots of unity, right? And yeah, you can associate each of these other roots with some integer 1, 2, or 3. Okay? So think about that. You should do that right now. Okay. So let's make some observations about what this formula is saying. So, the arguments of these m roots are 2 pi over m radians apart. Okay, look back at our case for m equals 4, right? We have each of these roots is 2 pi divided by 4 radians apart, right? Radians between 1 and I are pi over 2. I and negative 1, pi over 2. Negative 1 and negative I, pi over 2. Negative I and 1, pi over 2. Okay, so that tells you the answer to the question I just asked you to think about, right? You just increment, as you increment. When I say between these m roots, I mean for consecutive k, right? Okay. So, and in general, and they form the vertices of a regular m-bound. I should even say inscribed in the unit circle, right? Because each of them will have modulus 1. So they'll be one away from the origin, or the complex number 0. E.g., okay, let's look at the roots of zeta to the third equals 1. Well, we get 1. What other complex numbers can we find? Well, we find something about here. Forgive my sketch, which is zeta. Zeta 1 equal to e to the I 2 pi over 3. And down here, I get zeta 2 equal to, oh geez, really? Maybe it's too close together, sorry. So this point down here is zeta 2 equal to e to the I. What's the next interval here?
5 over 3.
4 pi over 3. Yeah. Right, this gives me an equilateral triangle. And you can do this for any n. Kind of cool. It gives you a way to construct the vertices of a regular m-gon. Be useful to us. In fact, I think it will be extensively useful to us. Okay, so I want to point out a particular nth root of unity. And this actually doesn't have a ton to do with what we're going to do. It's slightly related, but I want to point it out because it's of great importance in number theory, which is, I love it when branches of mathematics that seem mainly unrelated overlap, right? Number theory is the study of properties of the integers. Yet, it turns out by the use of complex numbers, we can deduce very profound properties of the integers, right? So this is along the lines of what I was showing you at the beginning of class today. It's like, oh, we can integrate things that we couldn't really do so well before. But this is even more surprising in a certain way. In fact, I can't really get into what exactly those profound things are. That would take us too far afield. But I just want you to have the exposure and know that it's related to the integers in a serious way. Okay, so let's let k equal 1 to get the nth root of unity. Let's call it omega sub m equal to e to the I 2 pi over m, which of course we can write in terms of cosine and sine as cosine of 2 pi over m plus I sine 2 pi over m. Here's the amazing fact. Then a complete set of m roots of unity can be obtained by looking we have 1, which is omega sub m to the 0. We have omega sub m, which is omega sub m to the 1. Omega sub m squared. All the way up to omega sub m to the m minus 1. Okay, so again, think back to our example of the fourth roots of unity. What was omega sub m in that setting? I, yeah, that was the fourth root of unity where k was equal to 1. Right? Okay, so this is great. However, graphically this was represented by the fact that it took us 3 steps starting at I to get back to 1. Right? All the powers of I turned out to be different fourth roots of unity. Where else is that the case? Negative I, yeah. Remember, it took us 3 steps. Of course, we took the steps backwards, but it still took us 3 steps to get to 1. So we traversed all of the roots of unity. Now, this wasn't the case for negative 1, right? It only took us 1 step. Okay, so such an nth root of unity is called primitive. That's because, in some sense, it generates all the other roots of unity just by taking successive powers. And, you know, think about this, right? If I take the nth roots of unity for some m, and let's say I get some theta here, and let's say this is omega m. Remember, all the roots of unity are theta apart consecutively. So when I take successive powers of this, I'm just going to move by theta. Right? And I'll continue to move by theta. Until I get all the way back around. Right? So I'll necessarily hit all the other roots of unity. If you believe my claim that all the other roots of unity, the nth roots of unity form a regular m-gon. Right? This is very geometrically motivated. Okay. So, right. Here's something that you can prove. That's kind of surprising. Prove that if we take the sum of all m minus 1 roots of unity, we get 0. Okay, now remember, I'm sticking with the notation that I gave you here, where omega sub m is when k equals 1. In fact, I could pick any primitive root of unity and this would be true. But for example, omega sub m is always a primitive root of unity. You'll always get, when you set k equal to 1, the powers of that root of unity will always give you all the roots of unity, mth roots of unity. Okay, so I'm going to give you a cop-out here and tell you the algebraic solution. And then I'm going to ask you about the geometric interpretation on the next homework assignment, which, by the way, I'll release on Friday after class, and you'll have a week to do it. Okay? Right, so here's the easy algebraic answer. Well, easy, hard. Here's the algebraic answer. I don't know, people think geometrically or algebraic, it's really up to you. Okay, so notice that what happens if I multiply omega sub m minus 1 times this sum that I'm interested in. How do I expand this?
You omega sub m all the way up to omega sub m to the nth power minus the original
Minus the...
or the right.
Oh, I'm sorry, I thought you were talking. Minus, I'm sorry, say that again?
Minus the original sum.
Yeah, right, so we just distribute both, we distribute omega sub m to this long sum, and we distribute a negative 1 to this long sum. And then we get a lot of cancellations.
To the m minus 1.
Minus 1, yeah, exactly.
Those two are the same.
Then the rest of the terms cancel because of this negative sign that we're introducing. When we multiply through by omega sub m, we're shifting the exponent up 1 on each of these terms. And then when we multiply by negative 1, we're turning all the other ones negative. So we get a negative 1, and then a negative omega sub m cancels with omega sub m times 1, for example. Exactly what you said. Yeah. So this is equal to omega sub m to the m minus 1. Now, what is omega sub m to the m? Is 1, yeah, because it's an mth root of unity. That means when you raise it to the power m, you get 1. So this is equal to 0. But remember, omega sub m is not equal to 1, because 1 is the nth root of unity where k is equal to 0. And we define omega sub m to be the nth root of unity when k is equal to 1. So these are definitely not the same, as long as m is greater than 1. Okay? So this implies that since this is not 0, this factor must be 0. Okay? Okay? That's not a particularly satisfying proof, right? I just told you multiply these two things together. But I'll ask you to elucidate the geometry on the next homework. Yeah?
You couldn't write that as a Taylor series, could you?
Okay, so this is actually an identity about numbers, right? Omega sub m is a complex number. What would you want to write as a Taylor series?
Because you could write that as a Taylor series of e to the 2 pi over m x.
So what are we talking about writing as a Taylor series?
So the sum, the 1 plus omega sub m plus omega sub m.
So if we let this be a polynomial, yeah. So that's another way of saying this. You could say that omega sub m is a root of the polynomial 1 plus z squared up through
Yeah.
z to the m minus 1. Yeah, so you can write that polynomial as a Taylor series, but writing a polynomial as a Taylor series is the same as writing a polynomial, right? Those coincide
Yeah, yeah.
in that case. Yeah, so just try to think about the geometry that's going on here. Okay? And you know, you might find it helpful to start maybe with the case of the triangle. M equals 3. Okay. So we started with equations of the form zeta to the m equals 1. In order to answer the question, what are the nth roots of 1? And now I've given you, I erased it already, but we developed a formula for that, right? So now, what can we say about taking the nth root of an arbitrary complex number? Well, unsurprisingly, it's also multi-valued, right, in the same way. But we can just as well write a formula for it. Okay? So, the general formula for all the nth roots of a complex number z is z to the 1 over m is equal to, okay, I'll give you a short little derivation here. This is the same as z times 1 to the 1 over m. Okay? Which is equal to, of course, by rules of exponents, z to the 1 over m times 1 to the 1 over m. And now I'm going to make a choice. I want to make a point to say that this last equality that I've just written, I'm going to make a choice for a particular value of the nth root of z. Namely, that first formula for zeta we wrote down. Okay? So I'm just going to write for the nth root of z, the nth root of the modulus of z, alright, nth root of the modulus of z times e to the I theta divided by m. Now, times my formula that we just deduced for 1 to the 1 over m, e to the I 2k pi divided by m. And then, again, by the usual rules of exponents, I will add the exponents on the exponentials to get a nicer looking expression. So all that is equal to the nth root of the modulus of z times e to the I times theta plus 2k pi all over m. Of course, I didn't want to say this in the middle of my equation, but here, again, I'm letting k run from 0 up to m minus 1. Okay, so again, this is becoming a motif, right? I'm choosing a particular value for z to the 1 over m. And then I'm using my arbitrary formula, my formula for all the mth roots of unity, to get all the mth roots of z. Okay? And I've made a particular choice here, but in fact, you could choose any mth root of z. And you'll still cycle through them all when you have your mth roots of 1 cycling through all the roots of 1. Okay? Okay, so let's just quickly do an example. What if I asked you to find all cube roots of z equal to root 2 plus I root 2? Okay. So maybe we should talk about this. What should be our first steps? If our aim is to apply this formula, what should we do first?
Find the modulus and theta of z.
Yeah, we should find the modulus and some argument. Right. Okay, so it's the modulus of 2 plus I root 2. This works out to be 2, right? Okay. And, well, just look at this in the plane, right? You just scaled version of going on 1, 1, right? That is to say, let me write this out. Since root 2 plus I root 2 is equal to root 2 1 plus I. Okay, so this is something that we've talked about geometric intuition of before, right? This just is a 45-degree angle or a pi over 4 angle away from the positive x-axis, and it's just, we're scaling it, so the argument is the same, right? So, let's let theta equal pi over 4. Okay, so then all we have to do is plug into our formula, right? That is to say, this implies that root 2 plus I root 2 raised to the 1/3 power is equal to, where did I write this? Oh, okay, here we go. The cube root of 2, right? We calculated the modulus to be 2, times e to the I plus pi over 4 times 3, right? Plus 2k pi divided by 3. And I've just distributed the 1 over m into this sum in the exponent. Okay, so my values of k run from 0 up to 2. Okay, so cube roots are when k equals 0, what do we get? We get the cube root of 2 times cosine of pi over 12 plus I sine of pi over 12. K equals 1. We get the cube root of 2 times the cosine of pi over 12 plus 2 pi over 3 gives us what altogether? 3 pi over 4, good. Plus I sine of 3 pi over 4. And when k equals 2, we just get the cube root of 2 times cosine of pi over 12 plus 4 pi over 3 gives us what?
17 pi over 12.
17 pi over 12, yeah. Plus I times sine of 17 pi over 12. Okay, there you have it. When it comes down to it, yes.
Do you care if we put it in cosine signs or just like the e to the power?
No, I don't really mind either way. You can leave it in exponential form or put it in sine and cosine form. Just a matter of taste. You know, I'll sometimes randomly do things in different equivalent ways just so you're more comfortable seeing them however they happen to be presented to you. But yeah, it doesn't matter how you present it to me, and any of the equivalent formulations are fine. Okay. Right, so, I don't want to say too much here, but you'll notice also that when you look at these 3 complex numbers in the plane, they form a triangle, right? So, yeah, this will be related to what I asked you about the geometric content behind this on the next problem set. Think about the triangle that this forms, that these 3, the cube roots of root 2 plus I root 2 form. So, good. That's pretty much all I wanted to say about mth roots of complex numbers. With that, we can start doing what I said we would do today, hopefully by the end of the day, which is talk about the technical requirements that we need to make and define before we actually start doing calculus with the complex numbers, with complex valued functions. Okay? In order to do this in a precise fashion, we have to talk about planar sets. Okay, so remember in calculus 1 and 2, we're concerned with functions that have nice properties in certain intervals, right? Open interval, or perhaps over here we might look at a closed interval. Right, and we formulate many of our results in calculus 1 and 2 in terms of functions that behave nicely in, or are defined in, open and closed intervals, right? Open and closed, of course, referring to whether or not these contain their endpoints. Okay, so when we begin to think of functions that take as input a complex number, remember, the complex numbers geometrically form a plane. And thinking back to single variable calculus, for the real numbers geometrically form a line. So it makes sense to formulate the results of calculus with real variables in terms of how a function behaves relative to a specific type of subset of the line, right? Intervals and open and closed intervals is mainly what we're concerned with. So in order to prepare ourselves to do calculus with a complex variable, we have to make analogous definitions to open and closed sets of the plane rather than the line, right? Because this line is our real number of inputs, is how we usually think of it, right? We have our x values for some function, f of x. Okay, but now in complex variables, our inputs are a plane, or I should say form a plane. Right, so that is to say, we might be interested in functions that are weird looking, right? Functions, if we say some function which is well defined on some complex input in this shaded region that I've drawn here, which is full of holes and may or may not contain all of its boundary. See that I have broken lines here? What can we say? Well, we have to make the right definitions in the first place. So that's what we're going to do for the rest of the time today, is start this discussion of what the analogous objects in the plane are to closed and open intervals. Okay? So, right, let's just start straight away. So what I'm going to do here is, this is these are actually the fundamental definitions that you first learn when you start to study topology. And they can be developed in much greater generality, but we're just going to stick to the complex plane. But the definitions are essentially the same in a more general setting. So what I'm going to do is just, I'm gonna give you a lot of definitions, but instead of giving them to you all at once, I'm just gonna go definition and then draw a bunch of examples. Definition, draw a bunch of examples. And that'll go on for the rest of the day and a significant portion of Friday. Okay, so let's start. Let's number them and see how far we get. So first of all, the set of points Z satisfying for a fixed Z naught in the complex numbers and rho a positive real number satisfying the modulus of Z minus Z naught is strictly less than rho. Everybody familiar with this symbol? It's a lowercase Greek r, rho.
I hate it.
It looks a lot like a P, right? Yeah, it's frustrating, but again, we're kind of stuck with it. When I write on the board, at least, you know, like, I try to make my rho's very distinct from my P's, but if it's confusing, let me know. Okay, this is called an open disk. Or sometimes circular neighborhood. Of Z naught. Okay, so remember, I think the first day we talked about how certain things we can write down in terms of the modulus cut out parts of the plane. We mainly talked about equalities. Here I'm looking at an inequality. This is to say, this is the set of all complex numbers that are strictly less than rho away from Z naught, right? So we're not just drawing a curve, we actually have a filled in circle, okay? So, e.g., we could take let's say this is the point 3 on the real axis, and let me just make a drawing. 1 is 5. Okay, so this will be the set of the subset of the plane indicated by Z minus 2. Oh, I'm sorry, and this is not 3, this is 2. 2. Oh, geez. Actually, let's stick with the picture I drew and I'll just change what I'll write. Z minus 3 is strictly less than 2. Right? So I have the point 3 at my center, and then all the complex numbers which are less than 2 away from 3. Notice, this will try to be my visual convention here. When I have a strict inequality, I'll try to make the boundary dashed, right? Because for example, this point 5 on the boundary, on the real axis, on the boundary of this disk, is not included in this set because 5 minus 3 is equal to 2, which is not strictly less than 2. So we'll put a dashed line when some part of our set is not contained in the picture. Okay. Of course, we can do this anywhere. Same type of construction. Let me take down here, we'll say is negative I. Okay. Here's the set cut out by the inequality. Z plus I is strictly less than 1/2. Okay. Very similar. And I'll just make special note of this set here, which is just Z strictly less than 1, which we'll often refer to, so we'll give it a special name, the open unit disk. Okay. So, definition 2. A point Z naught in C contained in a subset S of the complex numbers. Okay, I haven't necessarily said that S is of any particular shape. I'm just saying it's an arbitrary collection of complex numbers. Is called an interior point. Of S. If there is some circular neighborhood. Of C naught contained in S. Okay. So let's consider, e.g., let's let S be the set of complex numbers such that the real part of Z is greater than or equal to 0. And let's let Z naught be equal to 0.01. Okay, first of all, let's draw the set S. What is S? Yeah, it's the positive half plane, the positive real, or yeah, the half plane which has positive real part, right? It's everything to the right of the imaginary axis in the complex plane,
Including the line.
including the line. Right? Notice that this axis is not dashed. Thank you for saying that. Right? Because I have greater than or equal to. So this is not a dashed line here. So here's my point z naught equal to 0.01. Okay, well, I can draw a open circular neighborhood which is entirely contained in the set S, where, let's say, I come out to this point of intersection with the real axis is 0.02. Right? And I drew this irrespective of scale. I'm just saying that if I choose a small enough radius for my circular neighborhood, I'll fit inside of the half plane. Right? No matter how close I get to being on the imaginary axis without actually getting there, then I can draw a small neighborhood, a small circular neighborhood that's contained in S. Yeah.
So it's saying that as long as Z naught isn't on a boundary of S, it's an interior point?
Yeah, that's right. We haven't defined what boundary exactly is, but yeah, that's exactly the intuition. That as long as we're not on the edge of whatever picture we can draw, then we're an interior point. Okay? So let's just say, by contrast, okay, I didn't write a conclusion. Sorry. Then Z naught is interior point of S. Now, by contrast, Z1 equal to I is not interior. Right? Because let's say I go up here to Z1 equal to I. No matter what circular neighborhood I choose, that is to say, a circular neighborhood depends on two pieces of data, right? The center and the radius. I'm choosing the center. So what I'm saying here is that no matter how small I make the radius, I will always have points. Sorry, I should have made that dashed. I will always have points which are not contained in S, the half plane with positive real part. Okay? So no matter how small I get around this point, I'll always have these points which are not contained in S. Right? There's no choice of radius that will have my circular neighborhood around I be entirely contained in S for this particular S. Yeah. Okay. So let's all also just say, nor is Z2 minus 1 plus I, right? That comes out over here, right? Minus 1 plus I. And no circular neighborhood, or rather I should say many circular neighborhoods do not contain any part of S. So also not interior. And then it's kind of easier to see, or it matches the intuition with how we've set up our naming of terminology. Right? It's like, oh, it's not a part of S. The point itself is not contained in S. Right? Which was a part of the condition that we wrote down in the first place. Any point we consider is interior if it's part of S in the first place. And then you have to be able to draw a neighborhood around it. That's all entirely contained in S. Okay, so one more definition before we go. 3. If every point of S is an interior point, of S, then we call S an open set. Okay, so e.g., every open disk is an open set. And the example that we were just considering, S being defined as a set of complex numbers such that the real part of Z is greater than or equal to 0 is not an open set. Okay, so this is actually an exercise in the textbook. I'm not going to assign it to you, but I will ask you to verify this for yourself, that every open disk is in fact an open set. Okay, and we were just discussing why S from our previous example is not an open set, right? Because, for example, it contains the point Z1 equal to I. And there is no circular neighborhood around I, which is contained entirely in S. Okay, so it is not open. Okay, that'll do it for the day. I'm going to remind you once more about turning in your homework tomorrow, and have a good rest of the week until Friday. I'll see you then.
Something we had in high school actually.
Okay.
In classroom, we did one of these projects and each, we all had to figure out a topic to them.
Yeah.
I remember one group was a really interesting project on like an area formula, but the difference they were
Okay. Yeah.
and I don't know what they were called exactly. They made like some sort of formula like put the end on maybe by Z to like 1 minus 1 over n. That was very interesting.
Yeah, that is interesting, and that's I'm going to ask you a similar thing about how the relationship between the triangles, the equilateral triangle for the cube roots of unity, and the triangle formed by the cube roots of root 2 plus I root 2, for example. So we'll talk about that more. Yeah, great.
Quick question.
Sure.
I won't be here Friday because I got to go to the doctor's appointment
Okay.
in New Jersey. Any chance I could get the Zoom link? Because I know someone else is already doing this.
Yeah.
I can watch it from home. Is that okay?
Yeah, that's fine.
Okay, so if I email you, then just send, is that right? Or
Yeah, that'll be
That's
great.
not
Yeah,
okay.
just send me a reminder.
Okay, awesome.
I wouldn't want you to miss it. And if you do, that's okay. It's also recorded.
Oh, okay, awesome.
And once you have the passcode, which I'll
Yeah.
send you over email, you can look at the recording. If you happen to be like
Okay.
at the doctor during the
Cool.
time or anything like
I think actually my this is perfect.
that. Okay.
Okay, awesome. Thank you
Yeah.
so much.
No problem. See you next weekend.
Yep.